So, as second speaker, Professor Niayesh Afshordi from Perimeter Institute, and he will reflect on space-time.
Okay, thank you very much. So thanks everybody for staying around for the third day of the conference. I'm having a lot of fun. I should apologize. I just ran to someone with water, so I should apologize. Yeah, so it's all water everywhere here. Hopefully that'll lighten the mood. So let's see. So I was kind of dreaming about things that I cannot talk about in a physics conference because the physicists are too serious, or I'm not sure they frown upon talking about certain things. So I'm not entirely sure whether it's appropriate to talk about this in a philosophy conference, but I guess we'll find out. So the bulk of my talk is about reflections on the fundamental nature of space-time, but I'm going to start with a prelude, which is kind of, is as I said, it's kind of a stuff I wouldn't talk about in a physics conference, or at least whenever I've done it, people have really looked funny at me. So it's about the distinction between science and religion, and I guess I think it'll be clear when I get to it what I mean. Then I'm going to talk about three distinct possible evidences for nature of quantum gravity, which you may not have heard about, or may not have not heard about a lot. And then I'm going to say at the end, I'm going to try to put all this together and see whether there is a coherent picture about what the fundamental nature of a space-time could be. And actually, this is one of the things I believe you haven't heard about in the past three days here. So it's a somewhat different, not necessarily novel, but a different point of view. Okay, so let's start. So religion versus science. So they're both fantastic manifestations of human condition. It's hard to dispute that. However, I often wonder, and I guess the older I get, the more I wonder about this, can we disentangle these two manifestations when we talk about various human endeavors? And as a scientist, of course, I care about scientific disciplines. So when I think about religion, the kind of features, characteristics we talk about, elegance, there are prophets, there are disciples, there is epiphany, there is faith. This is not an exhaustive list, but it's the kind of things, features that you think of when you think about religion. Heresy, another thing. When you think about science, you think about predictivity, falsifiability, reproducibility, empirical evidence, and mathematics. So but I don't think these are exhaustive in any sense. They're just kind of things I was thinking about yesterday when I think about things that characterize science and things that characterize religion. Now I think it's fair to ask the question, what are the most powerful forces shaping a discipline? And in fact, I think I want to argue that is when we're thinking about disciplines, or scientific or non-scientific disciplines, really there is a spectrum between science and religion. And most things lie somewhere in between. So I made my own plot of where things lie. Religion is on the left and science is on the right. So stellar extraction is the most scientific, and my thing, superconductivity, is close by. On the left, there's Catholicism, Islam. I didn't put all the religions, obviously, here. And then all various scientific disciplines happen to lie somewhere in between. And the main criterion I use is basically, what are the main driving forces in the development of that discipline? Is it, so that's the question. What are the most powerful forces in shaping a discipline? Are these things like, elegance, prophets? Are you following a prophet? Do you rely on epiphanies for your next big thing? Are you faithful? Do you have to remain faithful to your disciplines? Are certain people banished because they are heretics? Or are these the most powerful forces? And I think actually it's kind of, I think, sometimes I hope that philosophers think about this more deeply than I have. But I feel that indeed, there is some level of that. So especially in disciplines that lack empirical data, there is more of the driving forces that drive religious disciplines that are at play. Where you do have empirical data, then you less have to rely on faith and on your prophets, basically, but you can just rely on data that to tell you basically where to go and what to do. Okay, so with that introduction, and it seems that everybody agrees with me because I don't hear any objections. Good. Then I can. I want to actually move on to the science part, and basically, I think my attempt at making the nature of a space-time more scientific, and that includes basically finding more empirical evidence. As I was hinting, the more empirical evidence you have, the more you can actually move from religion towards science, and that's kind of the goal I want to pursue and advocate here. Okay, any questions? Good. So let's look at the empirical evidence. So the kind of picture that I want to advocate here, it's not the only thing I work on. It's not necessarily what I believe is the fundamental nature of a space-time. I just find it to be the most promising thing I've worked on and I've considered. There are lots of other possibilities I've considered. And this one's, and I can, any other day I can advocate those ones. But today I'm going to advocate for you what I feel to be the most promising, as I think it addresses most of the problems that I'd like to be addressed in a theory of quantum gravity. And that's the so-called, what I call a quantum ether. Or this today I call it the quantum ether. And I want to argue that it's a minimal approach to make quantum gravity renormalizable or finite. And this was not done by me. This was most famously done by Petr Hojava, but many others have talked about it. And in some sense, it actually is something that comes out of quantum mechanics because time is treated very differently from space in quantum mechanics. But this was mostly manifested in Hojava gravity in the past 10 years or so. It can solve the black hole information paradox and explain black hole entropy. It could solve cosmological constant problems. It could solve cosmological horizon problems. I'm not going to talk too much about the first one, but there's huge literature out there on this. I'm going to talk mostly about the last three. And I would welcome interruptions. Okay, good. So let's talk about, so I'm going to talk about three different things. Echoes from the abyss has to do with black holes. Critical Big Bang is about Big Bang. And very wide vacuum is something you haven't heard about probably before. So we'll see. We'll talk about it when we get there. But it has to do with quantum fields and how they gravitate. So, so I'm going to start something somewhere that looks a little bit obtuse, but it's actually pretty simple. So this is a metric of a black hole. If I didn't have this term there, this would be just Schwarzschild metric. And all of you have seen it in one place or another. All I've done is to add an ether into a space-time and find a solution. Now this ether has a particular property which I call incompressible. So all it is a fluid that has pressure and no density, or has very small density. Actually, as long as it has a constant density, that's all that needs. And that's basically incompressible in the sense that, in a very similar sense that the fluid, that flows in a river is incompressible. That the density is constant, basically. And this is, in fact, there is an exact solution if you add the ether. And this incompressibility is something that I've worked on and written about quite a bit. I think that if quantum gravity does have an ether, it should be incompressible, or it's the best bet on the properties of that ether. And in particular, Hojava gravity had that, at least the original version. But that's something I'm not going to talk about too much today. Yes?
So you said that this metric is a solution.
That's right.
A solution of what?
So it's solution of general relativity plus an ether.
And does the ether stress energy tensor, does that violate the strong energy condition?
You mean strong energy is rho plus 3p? Is that what you?
Yes.
Yeah. Yes. This p naught is negative. Okay. Yes. And p naught, in fact, so p naught is an integration constant, which is the pressure of ether at infinity. And as you're going to see, I'm going to actually promote this to be dark energy, so it has negative pressure. So that's so there's empirical evidence for it. Yes. Okay. So and this f of r is just a function that you could solve analytically from for solving Einstein equations. Now, let me actually qualify. I think Robert asked what are the equations you're solving. And I mean, you could write any theory of gravity as Einstein gravity plus a fluid. It's just kind of a tautology. And then you just have to ask what are the properties of that fluid, right? And so what I'm advocating here is that if there is a preferred reference frame, then my best bet for the properties of that fluid is that it's a incompressible fluid. Okay, so we can talk more about that later. Now, the interesting thing about this solution is that actually this solution, it looks like Schwarzschild if you let this p naught go to 0, except that at infinity it blows up because this f of r thing blows up, and at the horizon this also blows up. So you can make this arbitrarily close to general relativity, except at the horizon, which is 0 here, if you go to minus very, very small values here, or if you go to the cosmological horizon far away. So yeah, it's the property that in this solution actually couples the geometry very close to the horizon of the black hole to the cosmological geometry. And it turns out that for any finite p naught at r equal to 2m, where the Schwarzschild radius is, you have a finite redshift, you don't have infinite redshift. So this doesn't have a horizon. And if you've heard about string theory solutions for black holes, there is a program called fuzzballs which share similar properties. And these are solutions that come from the string theory, and they don't have they don't have horizons. So I like to advocate this as at least a classical realization of fuzzballs, or at least as similar features in the sense that horizon, which emerges in classical general relativity, is in fact non-existent in this theory and in other approaches to understanding the entropy of black holes. Yes?
Sorry. So in the first one, it's not just that you don't have an horizon. You don't have anything inside the black hole.
That's right, exactly.
So this is also the case in what
that's the idea. R equal to 2m here is the end of the.
So the Pulsar solution doesn't tell you anything. It's not that you can go inside the black hole.
So there is a boundary of a space-time, right? So yeah, that's what it is. Yeah, there is no inside of the black hole. It's an empty black hole. It's literally a black hole. There's nothing inside. Okay, good. So other questions? Good. So there is something interesting we noticed when we came up with this solution, and this was quite, I guess now 8 years ago with my first student, Chandler Prescott-Weinstein, and Michael Ballow, a colleague, that if you actually, I told you that R equal to 2m that's the boundary of space-time, the redshift is finite. If you just set it to something natural you expect from quantum gravity, so the maximum energy of quantum gravity is Planck, if you expect Planck to be the right scale, and the minimum is the Hawking temperature, because that's the thing stuff that can get out of the black hole. If you say that that's the maximum redshift, then actually that fixes the value of p naught to a value which has a very sharp prediction. It is negative, and it actually happens to be the same as the pressure of dark energy that we observe. For masses of order 70 solar masses. Now, this could be 20 solar masses, depending on exactly how you define Planck temperature, if you include the spin of the black hole, etc. But the point is that, in fact, this would be a prediction that with the assumption of an incompressible ether, and the fact that there's a maximum redshift set by a scale of quantum gravity, you can actually predict the scale of dark energy for the black holes that actually exist in the universe. And most of the black holes that exist in the universe are in this mass range. The astrophysical ones, there are 10 to 20 solar mass, the ones that we observe, The LIGO ones that you've all heard about are 30, 40 solar masses. So that's the right mass range, that is within a couple of orders of magnitude. So that's interesting. And also, so the conjecture is that formation of a stellar black hole actually is connected to cosmic acceleration, given that we can get the right scale and the right sign out of that. And another conjecture was that the evolution of astrophysical black holes can actually lead to a dynamical dark energy. That part is a bit harder to put on solid ground, because it really depends on how you fit all these different black holes together. But here we had predictions back then about how the equation of a state of dark energy would depend on redshifts. The bounds are what you see. The dash regions were ruled out back then. And different lines are different models for formation of a stellar black holes over time. So basically the idea is that this is potentially a testable model for dark energy that's based on interplay of quantum gravity and astrophysical black holes. And it's not included in the effective field theory framework, just to mention that. Okay. Any questions?
So do you have to average over all of the, so each stellar black hole has a pressure?
Right. So that's a technical problem. So if you haven't, that's a problem I've been working on for, I guess, the past 8 years since we started this, and that hasn't been very successful. So right. So it's good, you can get this number very easily, but then if you have multiple black holes, what is the space-time in between? It's not quite clear. So I've worked on different approaches, it hasn't quite worked out. So I don't really know how to do that. That's been, I would say, disappointing. So I would have hoped it would be easier. But on the other hand, it's a hard problem. So it's a hard problem. Because it involves some unknown components, things like this, what is the quantum gravity. Of course, it involves all the messy known physics, like astrophysics and things like that, right? Okay, good. So that's the main hindrance to actually move forward with this program, to actually find a good framework to actually match the black hole spacetimes together.
So,
yes.
You said this. Why is stellar mass particularly interesting?
Well, because we know most of black holes are stellar mass black holes. That's how you form most of them. There are supermassive black holes, but by number and by mass, they are subdominant to stellar black holes, right? So it's just an empirical fact that most of black holes are within tens of solar masses. Good. And that number happens to give you the right scale of dark energy. That is, since surprising. Good. Any other questions? Good. Now, of course, that's the one prediction. We're not quite there to make this prediction sharp. But you see, another thing I mentioned, that there are no horizons, right? And that's important, right? Because at least until a couple of years ago, I thought this is something it would be very hard or impossible to test. Are there actually horizons of black hole? But then 2 years ago, basically Future happened, and then that was LIGO actually detected, to everybody's surprise, detected mergers of black holes. Even that, it wasn't clear whether that would tell us too much about the nature of the horizon. But then we actually thought about it, and other people at the same time were thinking about this. And it turns out observing gravitational waves from the merger of the black holes does tell you about the nature of the horizon. And the way it does is, actually, by the way, so these are basic data. I guess there's a new event. I haven't added this yet. But it's basically similar, kind of somewhere between these two events. So there are actually there are 3 events and 1 event candidate for mergers of black holes that has been observed. And around the same time that this data was released, it was pointed out by Vitor Cardoso and collaborators that, in fact, if you replace horizon by something different, like a firewall or a membrane, or you name it, some quantum gravity object, then what you do expect, in addition to the signal from the merger and the ring down, are late echoes that come out of the firewall. So what's responsible for late echoes? So the idea is that if you just have a regular horizon, there are some gravitational waves that go to infinity, and that's what you see, right, at like an observatory, for example. But there are also some gravitational waves that just fall through the black hole. In a standard general relativity, they would just fall through the horizon, and you would never hear from them. They would be just part of the mass of the horizon. it turns out that if you actually replace the horizon with some quantum mechanical object, part of that could be reflected, part or all depending on the nature of this guy. But generically, whatever you put here other than empty space, part of the gravitational waves could be reflected off of it and come back here. Now, it turns out when you look at space-time around black hole, there is so-called angular momentum barrier. Things that are inside of it fall into the black hole. Things that are outside of it go to infinity. So, but this actually looks like an echo chamber now, that if you have a firewall and then you have these angular momentum barriers from the standard general relativity, things can actually stay trapped in here. And whenever they come and go, get reflected and get back to the angular momentum barrier, you see an echo. And this is literally an echo, similar to when you shout in the mountains and then you keep hearing back what you say. So you see the main event, but if there's something here, you will see a first echo, a second echo, a third echo. And you can actually solve at least linear Einstein equations and see this is what exactly happens. So the main event is big, but then there are these late echoes that kind of periodically repeat and they get weaker over time. And the interesting thing is that these echoes are delayed parametrically, but not too much delayed. They're only logarithmically delayed. The reason for that is that the time that it takes for something to get to the horizon and back is infinite, right? But it's only logarithmically infinite. So if you put something Planck length outside the horizon, and that's the kind of scenario I was describing to you before, because when I was saying maximum redshift is Planck temperature divided by Hawking temperature, that's basically similar to saying that you put something, a Planck length outside where the horizon would be. Then you get a time scale that's logarithmically longer than the characteristic ring down time. So this is a time scale, basically. If you ignore the spin, this is exactly what it is. And this is around 0.3 seconds. So this picture actually doesn't have the time here. But this is around, let's see, 0.1 second here. I think it's 0.05 or 0.1 second. So the pictures that you see from LIGO actually might have it somewhere here. Yeah, you do see here, right? So this was the main event. So 0.3 second is basically this much. And when you look at the pictures, they actually don't show it because back then nobody knew or cared about that time scale. Okay, good. So we actually did go and look for it, and the person who drove this is a graduate student in Iran, Jahid Abedi, with another student, undergraduate at McGill, who was working with me at that time. It was last summer. We actually then basically made a template for the echoes, and it was kind of an ad hoc phenomenological thing. So we just took the original data from LIGO, original best-fit model to LIGO, and they truncated it and repeated it by the time scale that we expected. And the interesting thing is that the time scale you can predict exactly when you expect to see the echoes, because LIGO has measured the spin and the masses of the black holes. So you know exactly how long it takes to get to within the Planck length of the horizon and back. So this is the number if you ignore the spin, but if you add the spins, it would be a little bit longer, and then there's an error bar on it, and then different black holes will be different numbers. So we did it. We basically looked for the best fit, and just the data analysis primer. People who look at data, they look at something called signal to noise squared, signal to noise ratio, and this is maximized when the model fits the data the best. So you look for anybody who fits data anywhere, you look to maximize this. And if it's basically the model that gives you the maximum signal to noise, that's the model that fits the data the best. So we did that. We actually found that exactly at the time that you expect to see the echoes, you see a peak in signal to noise squared within 1% of that time. And 1% is roughly how well you can predict this thing. And the probability of getting just maximum as big as you get, this is for all the events combined, and this is just for the biggest event. The probability of getting something that big is basically around less than 1%, basically, just from random choice. So this peak, or this peak is basically 99% probability real. There's 1% probability that you get this peak at this point just due to random noise. And here what we did, we looked at random noise, how often basically you get something like this peak. This is just for one event, this is for 3 events combined. So the numbers we assigned to this will be 2 sigma, this is 3 sigma. Exactly what is the right number? Basically the idea is it's somewhere between 2 to 3 sigma. Because the exact number changes depending on exactly how you do the analysis. But that's the idea, that is around 99% probability this is real, at least if everything is as we think it is. And this is another manifestation of that, is that if you combine all events, look around where you predict the echo should be from Planckian physics and the LIGO data, and 1 is where it should be, and you see all these peaks of signal to noise, and you see the biggest peak is at 1, is basically very, very close to 1, where you predict it. And there are about 100 peaks here, so the probability of basically this happening just from random noise is around 1% or less, okay, of that in that neighborhood. So that's let's see, is that what? Right. So that's basically it. So that's the status. Yeah.
How did you? I mean, what did you assume about the noise? Is there just sort of some standard random?
Right. So the noise, the kind of the most honest way of doing it is basically look at elsewhere in the data. So the LIGO team released an hour of their data around the event. The event itself is, I mean, a fraction of a second. So basically the idea is that everywhere else is just noise.
If you put your noise thing in, can you say what that delta is? If you put that equation back on,
yes.
If you can tell us what one back.
But this 1 is being normalized by that, right? So 1 is, so this is basically time divided by delta t echo, which is predicted. Right?
Okay.
So if it's at 1, that's the prediction, right? And I mean, for different events, this delta t echo is different. That's why we kind of scaled all of them and added them together. So this is the best way to visually present this, I think.
So did you do the thing that you said that would be the best way to do it? I mean, using.
Best way.
I asked my question, right? You said the most honest way to do it.
Yeah, that's the way we did it. So these plots, this is basically how often you get this if you look at random points in data, right? So that's the histogram of that. So we see one where we predict, and then if you look elsewhere where we don't predict to be echoes, then basically the probability of getting something this big is less than 1%. So this is 1%. So this is somewhere around 1%. So that's the thing.
Those are both detectors?
This is both detectors, yeah. And I mean, I have lots of plots of this, but basically you can look at both detectors, both of them see the same signal. And now, random chance can do this. Random chance, so there's a 1% probability, and then depending on how you do this, you can change 1% to 3%. And now, the other problem is the LIGO noise could also change over time. That's another kind of Pandora's box that it's hard for us to know exactly what's happening with LIGO noise. But so there are things that can happen in data analysis, but that's the status as it is right now.
Therefore, is this assumed to be partly non-Gaussian noise? Or?
That's right. So exactly. So the Gaussian, there could be non-Gaussian. I mean, we know there is non-Gaussianity in LIGO noise right now. To what extent it's affecting this, it's controversial. So we've been in dialogue with LIGO people, and there's no question that there is non-Gaussian noise. In particular, there are these lines in the LIGO noise, and they actually move around. So, but exactly how much is important here, it's not clear. We didn't assume Gaussian noise. Okay. Yes.
I missing a very basic thing,
Yeah.
because so we are talking about a signal that. So I understand the fact that if you have some reflecting surface instead of a horizon,
Yeah.
you have some signal that comes and then comes back. But here we are talking about something different. We are talking about emerging.
Yeah.
So which one is the incident,
But-
the wave?
Right. And the merge, that picture is not a very clear picture when the black holes are apart. But in the ring down phase, you really basically have one black hole plus perturbation symmetric, right?
Okay, so I have this phase of the new black hole
Yeah.
that is oscillating probably
Right.
after the merging.
That's
and
right.
so is the echo of which
That's the phase we're talking about. Right?
Yeah, but the HO is a signal that is coming from where? And
So these oscillations, some of them would fall through the horizon in the standard GR, some would go to infinity. Right?
Okay, so they are the oscillation itself of the metric fluctuating around the new.
That's right, exactly. Now, I mean, this is obviously not the complete picture because, I mean, if you do have a fuzzball, there would be probably the original black holes have fuzzballs and they would merge. But that's a part of the picture that's much more complicated and we don't have right now. But so this is tantalizing, and I mean, there's obviously a lot more that can be done. But you see where I started from. I started from trying to explain dark energy. And I should say that this all started from actually Robert, because he wanted to explain dark energy by back reaction of fluctuations. And I convinced myself that cannot happen unless your fluctuations are very, very weird or big. And black holes are the biggest fluctuations you can have. So that all started back, 20 years ago. But this is where it has ended up. It started from dark energy into the horizon of the black hole. And then we look for these. And of course, this may go away. And there might be other reasons that there's something at the horizon of the black hole that has nothing to do with dark energy. But this is where the path has taken us. Good. So that's one piece of evidence for quantum ether. So let me give you two more pieces of evidence. Hopefully, they are less controversial, but somewhat less, more speculative. Now, about the Big Bang, some of you know a lot about it. I missed the first day, unfortunately. I couldn't make it. But just a very brief summary of what we know about the Big Bang observationally. So we knew at the Big Bang, or very close to the Big Bang, the space was uniformly expanding. There were small non-uniformities that were near scale invariant, with the scale vector fluctuating with the spectrum of 10 to the minus 10 times wavelength to the power of 0.033, plus or minus 0.004. So that's basically the best data we have right now. And basically what this means is that Big Bang was white but with a red hue. So that means that the fluctuations, they're almost the same on all scales. So for technical reasons, that's not what astronomers call white. But I think probably if people were to write terminology now, I would call this a scale invariant white, because all the scales are the same. And then it turns out that it's white almost, but it has a slightly red hue, a little bit more power on larger scales than the small scales. And these things you see from basically power spectrum of CMB. There are lots of data points that is very, very well fit by data. All this stuff are kind of acoustic physics that happen in late times. The primordial power spectrum was basically this. There are just 2 free numbers. And all the data we have are consistent with this. So that's a very, very simple picture of the Big Bang, and all the models of early universe, basically the primary goal is to explain this. Now, where does the ether come in here? So it turns out that this is a scenario called thermal tachyacoustic cosmology. So if a speed of sound goes to infinity, and that's related to the incompressibility. So the idea is that at the very early times, signals propagate infinitely fast. And this is, you could also notice that this has to do with, if you have a theory of quantum gravity, which is normalizable, for example, Hojava gravity, which does break Lorentz invariance, this is something that does happen naturally at high temperatures. So this is something you expect when you break Lorentz symmetry and you want to make gravity finite. This is basically what you bargain for. If you require that it goes to infinity very rapidly near Big Bang, and this is actually how it should look like, the sound horizon, how far sound travels, it's very, very small in a standard cosmology, but suddenly it should get very, very big as you approach the Big Bang. Right. So that's this. I think actually this is sound speed times the Hubble radius. I'm not entirely. I think sound horizon maybe not the right terminology for it. But that's the idea, that there's a very early time somewhere where the temperature of the universe is 10 to the 15 GeV, sound speed suddenly shoots up. And that can solve the cosmological horizon problem because everything is moving very, very fast. Everybody can talk to everybody, and things can become homogenized. It turns out that this behavior with thermal initial conditions gives you near a scale invariant power spectrum, and this was first noticed by Zhao Magoeja. And there's no need for reheating because this theory, we know Big Bang was hot, inflation was cold, so all inflationary models had a reheating period. This theory was hot all along, so there is no reheating. So it's a very, in that sense, it's a very minimal model for the Big Bang. And it turns out that we found, working with Zhao later, last year, well, last couple of years, we found that there is a very unique action that could be fixed for basically just two principles. One is that speed of sound goes to infinity at early times, and you require that it's consistent with general relativity. That basically fixes this action, these two parts of the action. And then if you secondarily require that this theory is a scale-free, or as a scale-free as it can be, and or it has ADS2, and this is somewhat technical, but it's very elegant, and from my point of view, technical point. It has ADS2 time geometry, so this part of the action, this is the kinetic term, it looks like an ADS2, a two-dimensional anti-de Sitter line element. Either of these two assumptions actually fixes these two parts, this part of the action. So basically, this combination of these two requirements fixes this action uniquely up to one scale, which I call M here. And as I told you, there is no reheating period because this was theory was hot all along. So it actually predicts a unique power spectrum with a unique spectral index. This is the color of the universe that our theory would predict. And this was just for your collection. This is the observed one. So yeah,
Chi is space length?
Chi is a field. Yeah, is a scalar field.
Just a scalar field.
Yeah, so you can think of it as a field that represents sound waves in our universe.
So its gradient doesn't need to have any particular signature.
Well, it's a cosmological field, and we only look at linear perturbation theory. So its gradient is time-like. Right? I mean, for very large perturbations, I think it is good. Well, yeah. So I think I'm not sure for very large perturbations there could be a limit on its gradient, right? But we don't look at very large perturbations. Yes.
But chi waves are propagating outside the light cones.
That's right. And this is how they propagate. This is the sound wave. So this is a standard cosmology sound horizon. So basically, the earlier times it had a smaller sound horizon. But if you actually go to very, very early times, then the speed of sound shoots up. And this is something that we worked on, my collaborator Azal Geshin's-Jani and Daniel Chang almost 10 years ago. Actually, more than 10 years ago, we pointed out that actions with this square root, without this extra piece, have this property that speed is infinite, basically. Speed of propagation is infinite for them. If you add something small to it, then the speed is very big, but not infinite. But the idea is that at early times, you just get a square root kinetic term, and that's a speed of sound going to infinity. Right. That's the property. So basically, this exponential goes to 0 at early times, and you got just a square root, which is a unique action. In fact, this consistency fixes action uniquely, and yeah, it's right. The speed of sound is infinite in that limit. Okay.
So the gradients are pure functions of chi, or almost constant. The dimu chi.
Well, no, they're not constant. You have to solve the equations. So there's the background plus perturbation. You have to solve them consistently, and that's what we do. But the interesting thing is that basically these two requirements uniquely fixes this action to one scale. And if you set the amplitude of fluctuations based on, use that to set this scale, then you have a unique prediction for a spectral index, which is consistent with data. So I would argue that, now obviously I'm biased, but I would argue that this is the most predictive theory of Big Bang, as far as I know. So. Because it doesn't have reheating, and it just gives it one number for a spectral index. And it's consistent with data. So it's the most predictive theory of Big Bang that has not ruled out yet, I should say. But it very well may be ruled out soon. Yes.
So the waves are kind of propagating to infinity along like the surface,
yeah. Constant field surfaces or constant. Yes, that's right. and they propagate infinitely far as you approach them. If you take a sound wave and go back in time, you see it's traveling with first the speed of light, but it gets faster and faster, and then would travel infinitely fast as you, or move infinitely infinitely far as you approach the Big Bang. That's this plot, right? This is how far. This is how far. Sorry, I went too far. It would go infinitely far, and it moves infinitely fast. So they both happen at the same time. So this is another. So notice that speed of sound goes to infinity here. So I'm here. I'm also talking about. So you can think about chi here as. Well, so whenever a speed of sound becomes bigger than 1, that means that you have a preferred reference frame. So, and that's another manifestation of the quantum ether. So that's the second piece of evidence.
So, but you still have light, normal light moving in the usual light cone. It's this sound that is.
Yeah, well, we don't talk about that. It could be light also could move on the same thing. So, I mean, the version of it that Joe wants to talk about is this biometric theory that there are two metrics, one for gravity and another for all the matters, including light. So in that sense, then the light does go infinitely fast as well. But for the predictions here, we don't care about light. We only care about sounds because that's the only thing that we see.
So this chi field somehow interacts with all the other fields to set up the density perturbation?
It's like it's a plasma density, right? So you have kind of a primordial goo of everything, light, quarks, electrons.
Right, so it's coupled to everything, and then that's what determines that's how it gets the imprint.
So basically, it would be the temperature, right? So that's the only degree of freedom you need if you have high temperature and thermal equilibrium, because the temperature fits everything, right? Good. Okay. Good. So that's the second piece of evidence, and I know I'm running. I thought I did start a little bit late, so maybe. What do you think?
15 minutes.
Oh, that's good. Okay. Guess I'll have plenty of time. So this, the last piece of evidence, it's actually kind of disjoint from the first two, but it's very weird and bizarre, and there's something we discovered in the last couple of years again, and we don't really know what it tells us about quantum gravity, but it's very different from any other piece of evidence we have. So this is a plot that, with the exception of this red box here, we all have seen it, and this is something a particle physicists talk about a lot. This is so-called hierarchy problem. So basically, there are three sets of scales in high energy physics. There are the cosmological scales, dark energy, for example. Neutrino mass happen to be a similar scale. There are particle physics scale, like a Large Hadron Collider, electroweak, Higgs mass, things like that. That's around a TeV, tera electron volt. And then there is a Planck scale or grand unified theory scale. This is around 10 to the 28 electron volts, or Planck mass. So, this hierarchy between these three different scales is a problem in basically our problems in particle physics. Particle physicists think that this cannot be explained in any so-called technically natural way. And that means that basically if you take an effective field theory and you, then basically these three scales should be the same. So the biggest one, and is the oldest one, is the so-called old cosmological constant problem that suggests that basically this 120 orders of magnitude discrepancy between dark energy as a scale and Planck scale, that's not natural. But if you forget about gravity, then there is a Higgs hierarchy problem, which is the hierarchy between the scale of the Higgs mass and the highest scale you have in the theory, say a string scale that we heard about, or the Planck mass. That's a problem. Now, I want to talk about something that's now this is a problem that high energy physicists have kind of learned to deal with, and there's a lot of activity. Like supersymmetry is invented to solve this problem. Nobody really has a good solution for this problem, but it is no particle physicist that should have a good solution for this problem. But I want to tell you something which is kind of fits in here, but it's a very, very different nature. And it's actually on the same scale as the Higgs hierarchy problem, but it comes from somewhere very, very different. So the punchline of it is that gravity is different. And this sounds like me repeating myself, that UV physics is coupled to IR physics. In larger scales and small scales are coupled to each other. The most striking thing is that if you follow the arguments I'm going to give you in a second, there shouldn't be any new scale in quantum field theory plus general relativity, and by new scale I mean any new massive particle, above a scale of tera electron volts. So let's see all the high energy colliders, they're not going to see anything more than they have seen so far. At least not at high masses or energies. Now, what it's going to point to, it's going to rule out higher scale supersymmetry, grand unified theories, almost all inflation models, everything that requires a scale bigger than a TeV. I mean, unless you push things in a funny way, they are all ruled out. And the things that could be possible in this, the constraints that I'm going to give you in a second, if you have TeV scale quantum gravity, large extra dimensions, or some other weird non-perturbative effect that happens. Doesn't happen on Planck scale. It may happen at the Planck scale, but it's not the standard perturbative things like a string theory that people, well, I shouldn't. There isn't a standard quantum field theory particles above the scale of TeV. So that's what I want to say. Now, what are the constraints? So what the thing that we talk about is basically the vacuum of the quantum field theory. So quantum fluctuations fluctuate. So that means that if you look at the 2-point correlation function of the stress tensor, it's not the same as the product of the 1-point functions. So this basically just says that the variance of the stress tensor for a quantum field is non-zero. So this is basically the analog of the cosmological constant problem, but for the covariance of the stress tensor. So we asked what is the analog of that if you worry about the gravity of these fluctuations. And then we asked whether these fluctuations can actually gravitate, and that's something that we did a couple of years ago. So this is a little bit technical. I'm not going to go through it in detail, but it's just basically plugging it's a dimensional argument through fluctuations of vacuum energy, plug it into Einstein equation, and find metric fluctuations, and then you find that, in fact, the metric fluctuations blow up in the infrared. So that's kind of weird, but that's what it is. If you just plug the correlations of the stress fluctuations into Einstein equations, and this is linearized Einstein equation. Look at the solution, what you find is that, in fact, they get big at larger scales. Right, so they get big on larger scales, and this blows up at the 5th power of the high energy scale. So it goes at some high energy scale to the 5th power divided by m Planck to the 4th times k. And if you plug in some scales, you see that this becomes of order 1 as at the scale of lambda to the 5th divided by m Planck to the 4th. So if you want this to be less than, this infrared scale to be less than a Hubble, then that tells you that the UV scale should be less than PeV, which is 1,000 TeV, or 2,000 TeV. So that's kind of the dimensional argument. You don't have to follow this, but then the idea is that this gives you, in fact, this gives you, this is the gist of the idea that if you have a small scale fluctuations of a stress tensor of a quantum field, it gives you larger scale fluctuations of gravity. And if you have any probe of larger scale metric fluctuations, like you do in cosmology or you do in pulsar timing, then that actually can put a constraint on your UV physics. And that's what we did. And in fact, if you look at the pulsar timing, that gives you the strongest constraint. So the idea is that there are pulsars that are happens to be very, very good clocks that happen to be a few kiloparsecs away from us. And you can observe them and see that they're very, very stable clocks. But of course, since their signal has to propagate to us through the space-time, then the space-time cannot be fluctuating too much. Otherwise, you wouldn't see a very stable clock. And we can predict how stable it should be given these fluctuations that I was telling you for massive particles of mass m, distance of pulsar d, and frequency observation f. And so this is the formula. It goes as the 5th power of mass. There's m Planck to the 4th. It has all the same properties as the dimensional argument I gave you last slide. And in fact, it puts an upper limit. Given the most stable pulsar we have, it gives an upper limit on mass, which is 600 GeV. For a scalar, for other type of particles, it's a stricter bound. So this is the third piece of argument, that it tells you that whatever happens in the quantum theory of gravity, if this is real, it shouldn't screw up these constraints. So you shouldn't at least have massive particles or things that look like massive particles above a 600 GeV scale. And what that means, so a standard model, the most massive particles are Higgs and top quark. They're not quite that massive. So we cannot see that signal right now, 125 and 173 GeV. But anything beyond that is around 600 GeV basically is ruled out, and there is basically very little room left. So that's, sorry, there was too much stuff, but so let me just leave you with convergence of these different ideas, and I don't really have a good coherent picture. I think my first punchline is quantum ether fundamental to space-time, and I think I gave you three pieces of argument, test of the quantum ether, or predictions of quantum ether for a Big Bang, for black holes and dark energy that have very different tests that, depending on how you look at the data, they're either supported by data or are consistent with data. The second piece of evidence, and I'm not entirely sure how to fit it to the first one, is that there could be no new particles at higher energies in colliders. That doesn't necessarily mean that there are no Planck in physics, but it just means that whatever happens at high energies shouldn't look like massive particles. Now, another question, is there a fully consistent framework that basically explains all this and be consistent with no new particles at higher energies? And that I don't really have a good answer. Okay, thank you.
Yes.
So I wanted to thank you about your talk. I had a question about the barriers that we were talking about when the black holes emerged,
Right.
and there was an echo that went into space. So I wanted to ask that, well, the oscillation will continue to infinity, I guess, because the scattering is... Okay, so I had a question that if an echo from another black hole or from another place comes and it crosses the barrier...
From a different black hole?
Yes.
Yeah. It would be a tiny, tiny signal.
Does it affect the actual oscillation of the particle?
No, any perturbation from other black holes is so tiny by the time it reaches this black hole that it would have almost no effect, basically, 10 to the minus 20 or something like that. So the answer is no, it would be an unobservable, tiny effect. And it just has to do with linear superposition because, I mean, gravitational waves are a small amplitude. You just add them on top of each other. And if you have gravitational wave from one black hole getting to another black hole, it's so tiny by the time it gets there.
But basically, it can pass the barrier and it can have...
It can be reflected and do all those things. It's just it's a very, very small effect, yeah.
So I was just trying to understand how the three things relate. So you've got one, a chi field that leads to the infinite sound speed in the early universe, the incompressible fluid that gives you the order of magnitude of dark energy, and then a modification of the event horizon.
Yes.
In particular, the third one, it wasn't clear to me. It looked to me like that was a whole class of modifications for the event horizon.
I mean, you could just look at it on its own. I mean, for the horizon of the black hole, right?
Right.
But my approach.
So how is it that the quantum ether ties all those three together?
Because that's a concrete solution that does modify horizon within a Planck scale, right?
Okay.
So that was the metric I wrote down for you.
Right. And then is that the same modification that's relevant for the sound speed going to infinity in the early universe?
No, not tomorrow. So, so that's part of this question, is there a fully consistent framework? So they both have this speed of sound going to infinity in common, right? But I'm pretty sure these are not the same degrees of freedom. And it's, I mean, at some level it's understandable that obviously not everything propagates with the speed of infinity today, right? You have light and matter and things like that, right? So, so basically one of the challenges, you could say, of this program is, obviously Lorentz invariance is a very, very good approximation to physics as we know it right now. So if there does exist a Lorentz violating quantum ether, it's very, very well hidden now. So it might only represent itself in very extreme situations like horizontal black hole. But we don't have like evidence that in our face right now of this quantum ether. So it's very subtle effect right now. But at very, very early times, that's the idea that it was not so hidden and everything was interacting strongly. So you had this kind of composite fluid, the chi field, right? So the idea is that basically the quantum ether right now is the remnant of that has basically decoupled from everything else. That's why we don't see it. But at the early times, everything was coupled, and you had this basically. And if you go to very early time, the speed of sound of everything basically goes to infinity. And that's what you require to, say, make gravity normalizable at the Planck scale. Right.
Jessica?
I have 1.5 physics comments and a philosophy question.
Okay.
So, first the physics comment, the first one at least. So you have this model for the Diekon, but you are not really providing any fundamental model for this surface. You're just assuming that some, maybe quantum gravity effects provides this surface at the horizon. But you were mentioning the firewalls. But so
fuzzballs.
You were mentioning also firewalls.
Did I?
Yeah.
I think I tried to not mention it, but.
You were mentioning fuzzball at a certain point, but then there was another slide with written firewalls.
Sorry, okay, so maybe I did.
If you take back the firewall, then I take away my comment as well.
Okay, I'm happy to take it back, yes. So I think I've started to move, I started to stop mentioning firewall because I know it invokes negative feelings. And
no, okay, but my comment about the firewalls is simply that it's not something that happens in a place, it's something that happens at a certain point in time. So
yeah, I mean the thing with firewalls is such a I shouldn't call it, it's a fuzzy subject, so everybody has their own idea of what it is. So that's why I want to not talk about it.
Okay, let's go away from this. The other half comment that is actually a question. So, is the ether always choosing a preferred frame and therefore breaking Lorentz invariance? Because if so, you were answering to the previous comment, saying, okay, this becomes relevant in the universe, but we have observations in cosmology for the propagations of the primordial fluctuation that tell us that you cannot have such a thing in the universe.
What type of observation?
Using effective field theory in cosmology, in fact.
Well, I mean, I showed you.
For Rava-Lishvitz, this was studied, but for Rava gravity.
I would dispute that, so I don't know. I mean, I think I've kind of written papers on modalities cosmology and studied literature as much as I could, and I would say that either not existent or wrong. So.
Okay, let's discuss more later. The philosophy question. So you were presenting this very funny slides at the beginning about religion
versus science.
So my question is, okay, so you are presenting us some way to do physics in which you take a phenomenological approach. So you say, okay, I have this phenomena. I want to try to understand this phenomena. I try to guess some phenomenological model that describe this as best, and then I call this the most predictive theory that I have. So why this is more scientific than starting from first principles to some few principles and trying to derive phenomenology from there?
This is a very good question. So I think I was not clear. I don't think you should just look at the data and then build your theories just based on that. So I think there is the best theories are the ones that come from interplay of theoretical insights and observational data. And the more you go back and forth between those two, I think the more developed or mature a theory is. And I think what I was trying to tell you is where I started from, and then how I ended up in data, and then how I got back to theory and data. So there is actually, I guess you could say they're going back and forth between theory and data. And I think that's what's required for a successful scientific theory.
You did not have your theory up there, right? I mean,
Well, it was an idea, which is quantum ether. So, yes.
And what is the fundamental principle that from which you move in order to say this?
So I think the fundamental principle is that there is a preferred frame, and the speeds of propagation at high energies go to infinity in that preferred frame. So that's kind of the fundamental principle.
So you think that but we don't have to take so seriously general relativity with this respect?
No, of course. I mean, it's general relativity if it's the data. So I guess we had that's the less fundamental theory, right? And the quantum meter is a more fundamental theory. So, right? So more fundamental theory has to, I forgot the terminology,
Isn't that
reduce
a
it.
fundamental preferred frame adding more structure? We had already a theory that is more generic.
Well, adding more structure, yes, it's more structure than general relativity. No, but there is more free parameters, I can't tell, but I'm not entirely sure. I think it's just it's a different framework, but I mean, certainly the way it is looks more complicated than general relativity, but of course general relativity doesn't give you everything you want, right? Does it?
Yeah. Doesn't give me comfort.
Yeah.
Okay, let's thank the speaker again.
Thank you.